Okay, altimeters. Altimeters. We're going to talk about altimeters, and we're talking about types of altitude as well. Kind of like we have different types of airspeed. There's actually different kinds of altitude as well. So we're talking a little bit about how altimeters work and vertical speed indicator, which is a different gauge as well. So here we go. So let's talk about types of altitude first. We have indicated altitude. It's read right off the altimeter. Indicated altitude is read right off the altimeter. We have pressure altitude. Pressure altitude is when you just set your altimeter to 299 or 2. That's standard pressure. That number should ring a bell in your head. But we set it to 299 or 2, and then it's read off the altimeter. And it's used a lot in performance charts, and we'll talk more about that when we get to performance charts. But basically, if you want to know it, you're sitting in the plane, you can dial it into 299 or 2. There's also a chart you can read to convert it as well. On a standard day, you can convert it using the inches of mercury per thousand feet calculation. Like I said, we're going to get to all that in another lesson if we haven't already talked about that in class. But those are used in performance charts. Then we have density altitude. And density altitude is pressure altitude, not indicated, but pressure altitude adjusted for temperature. Hot air is thinner, so it's like high altitude air, and your aircraft's performance is degraded. We're going to talk a lot about density altitude in class. It is one that really gets a lot of pilots, particularly here in Utah, where I live, because we have high altitude airports, but we also have really hot air at these airports as well. And as we learned last lesson, as you go up in the atmosphere, the air gets thinner. But also, as you heat air, it gets thinner. So I could be at one airport altitude. Let's say I'm at an airport of 6,000 feet, but on a hot day, the air could be so hot that the air is like the air at 9,000 feet. So therefore, my airplane's performance is degraded. I don't get as much horsepower. I don't get as much lift on my wings and those kinds of things. We're going to talk more about that in class, like I said. But I just wanted to really push that point home. That density altitude is one that you definitely want to calculate before flights. And we're going to talk about some accidents that were caused but due to density altitude. And then we have calibrated altitude. So you have to have indicated to figure out pressure, and you have to have pressure to figure out density altitude. You really only need indicated to figure out calibrated altitude. This one sort of is kind of an outlier with this one. But this is indicated altitude corrected for installation error. Now, we talked about calibrated airspeed in the last section, and we talked about how you have installation error with some of these gauges. So they have a little chart that corrects it. Well, we have the same thing for calibrated altitude. And then we have two other ones that sort of don't really play into either one. They may have more to do with indicated altitude than anything else. But we have one called true altitude, and true altitude is the actual height above sea level. So in Park City, we're between like 6,000 and 7,000 feet, and so that's above sea level. So if you say you're up in the mountains and you're at 7,000 feet, what they're talking about is 7,000 feet above mean sea level (MSL), and this is used on aeronautical charts a lot. So when we start looking at airport elevations and mountain elevations, when we get to our sectional charts, we'll be talking about true altitude on those. And then we have absolute altitude. I really don't use the term absolute altitude. Instead, I use AGL, above ground level. That's what I call it. So if you hear me say 500 AGL or 4,000 AGL, I'm talking about absolute altitude. This is your height above the Earth's surface. So if you're flying along something and there's like a mountain and you fly along that mountain and now you went from 3,000 AGL to 500 AGL, right? Because the earth changed, but you stayed at the same altitude. So you're always talking about how high you are above the ground. That's AGL, or absolute altitude. Alrighty, this is an altimeter, and we're going to learn how to read this in class. But just so you know, the big, long, skinny arm is hundreds of feet. So right now it's pointing at about 180 feet. This would be 100 feet. This would be 200 feet. It's pointing at this line right here. That's about 180 feet. This is thousands of feet. So this is not quite above zero. So we haven't passed 1,000. But if this was pointing at the 2, we would say, oh, 2,180 feet. So you got to kind of read each hand individually. And then this one's tens of thousands of feet. So this one is at the 10,000 mark. So it's 10,000, 0, so 10,180 feet. This is called the Kalsman's window. This is where you set the pressure. Remember we talked about like the pitot system. Well, the air temperature and pressure changes every single day. So we actually set the temperature right here with this window. We use this little knob right here and we turn it and we can set the correct pressure that we get from the weather briefing or the weather system that we're listening to for our weather. We set that in this window and then we have the correct altitude. So basically you're correcting this altimeter all the time for the air pressure that you happen to be flying in. So like I said, what is this one? 10,180 feet. So we're going to do some of these in class. This is from a integrated flight deck. This one's really easy. You just read it. This is at 1,460 feet. Okay. So this is what it looks like when we fly our simulators, and if you fly a G1000 type aircraft, we call this we just call this the altimeter, just like the other ones. Just so you know, we're gonna get to this later. This one on the side, this is the vertical speed indicator as well. Where is it on here? There's your barometer knob. That's how you set the pressure. And you set that pressure right there, and then this is the altimeter. So the altimeter is on the right. So how does the altimeter work? It does not use the pitot tube, it just uses the static port. And the static air comes in and we have these things called aneroid wafers, and they get pushed up and down, which turns the linkages, which then turns the hands. So when you're setting this knob, you're really just calibrating these gears in here so that when they start to turn, they have a good place that they've started from. Now there are types of altimeter errors you should be aware of. Number one, you didn't set your altimeter properly, so therefore you don't really know what your altitude exactly is, so you should reset it. Number two, flying from high to low pressure. We always say look out below because you're actually lower than indicated. So you fly out of an area of high pressure into an area of low pressure. You might want to look out. We say look out below because you're actually lower than you thought. Here, let me show you. Flying from warm air into cold air. I'll show you a picture of that, I think, in just a second as well. So like here it is for temperature. You're flying along inside your flight deck. You're looking at it says 5,000 feet. It says on your altimeter. And you're still flying along. And look how this plane is going down. But the pilot's probably still looking at his altimeter, still saying 5,000 feet because he didn't reset it. So you want to make sure that you're always setting your altimeter I usually set mine about every 30 minutes or anytime I feel like I've changed weather systems or anytime I get an update from air traffic control. They'll tell you that as well. They'll say, you'll check in, we'll say like Salt Lake Center, Bonanza 1234 Papa Hotel, 5,000 feet. And they'll say, Roger that, Bonanza, altimeter setting 3012. And I'll just make sure that I have 3012 or whatever set into my altimeter. All right, then we have a vertical speed indicator. This is a very handy one for really fine-tuning your takeoffs, your landings. It's very useful as a private pilot flying in the mountains because if you're trying to figure out, like, I'm going to be over those mountains in 10 minutes and I need to gain 5,000 feet. So that's about, a couple hundred feet a minute that I need to climb in order to make sure I'm there. And you can figure those things out and then use this gauge to make sure you're going to be at the altitude when you think you're going to be there. Also descents. I'm descending into an airport and I want to say, okay, the traffic pattern altitude is 1,000 feet and I'm at 12,000 feet. And I've got about 12 minutes to go. So that means that I need to lose about 1,000 feet a minute so that I make sure that I'm there. So I can do my descent and be checking with my vertical speed indicator as I use it. To be honest, as a private pilot, I use this some because my flight instructor taught me to use it, and I was pretty good with it, but I really used it a lot in my instrument training. I got really tight on this vertical speed indicator. Now I use it all the time. It's one of my gauges that really I use to calculate my performance in flight in real time. So it just takes some practice to kind of learn to like what its use is and what it's when it's useful and what its purpose is. But let's talk about what it is. 5 things you want to know about the VSI. Number 1, it displays the rate of climb going up or the rate of descent going down. Number 2, it displays in feet per minute. It displays in feet per minute. Number 3, it measures how fast the air pressure is changing through something called a calibrated leak. Has some lag, meaning you have to wait for it to stabilize. Just don't, if it says 1,000 and it just moved there, just give it a second. It might need to stabilize a little bit. It's letting the air out of the calibrated leak or letting some air in. It's very useful for approaches and takeoffs, also climbing en route and descending en route. All right, so we have a needle. It's usually pointing at 0 if you're not climbing or descending. In this case, you're climbing at about 200 feet per minute. This shows you vertical feet per minute in hundreds of feet. This is 1,000 feet per minute, 500 feet per minute, 500 down, 500,000 down, 2,000 feet per minute climb or descent. Typically, when I'm approaching, coming into land, I'm about 500 feet per minute down. On a climb out, a typical gauge is 500 feet per minute up, but just really depends on what you're trying to do, what speed you're flying, what's the density of the air, all those things. This is how it works. You've got the calibrated leak here. This is attached to this static port, and you have direct static pressure pushing on this, and then the air leaks out of it at a certain rate, and as it does, this changes the shape of this diaphragm here, and it pushes up and down, pushes on the linkages, and shows how it's moving. So as the air is moving in and out, it's changing the shape of this diaphragm, which causes the VSI to move. All right, so last thing we're going to talk about with the pitot system for this section is instrument errors. Okay, these are instrument errors. They have some questions about this on most FAA knowledge exams. So let's talk about instrument errors, because they can have errors in them, and you need to know how to sort of deal with those if you ever do run into this situation. The first one is, what happens when that pitot tube gets blocked? What happens when it gets blocked? How do you think the instruments are going to behave? Think about that for a second. Okay, first of all, which instruments use the pitot tube? Well, the only one that uses the pitot tube is the airspeed indicator. So it's the only one that's going to be affected by it. So a blocked pitot port, but the drain hole is open, it decreases to 0. So what's a drain hole? Well, you've got the pitot tube, and the air is coming into the pitot tube, and it goes up and into the air lines, into the airspeed indicator. Well, in this case, in the back of the pitot tube, there's a little drain hole for water to drain out, because you might fly through rain or something, and it just drains out. But so if the pitot tube is blocked, but the drain hole is not, all the air in the airspeed indicator is going to leak backwards out and through the drain hole. And so you'll watch your airspeed indicator just decrease down to 0. Even though you're flying through the air, you know you're flying through the air, your airspeed indicator says 0, blocked pitot port. Here's a better picture of it than I was trying to show you. You got a blockage here where it's black. Here's your airspeed indicator. Here's the plumbing, and the air just leaks back out through there. So therefore, all the air leaked out of here. So there's no ram air pressure coming in. So it figures, hey, I'm going 0, even though you know you're going through the air at way faster than 0. So that means you have usually a blocked pitot port. All right, so what happens when the blocked pitot port and the drain hole, they're both blocked, or maybe there's a block inside the line, something like this, like you have a blockage here, and the pitot tube is blocked, or the drain hole's blocked, both of them are blocked. Well, basically it'll act like an altimeter. That's what will happen. The airspeed indicator will act like an altimeter. Let me explain a little bit about what that means really quickly. I'll explain more about it in class if you have more questions. But when you climb in an airplane, your airspeed goes down, just like rolling uphill on a skateboard. If you were just going on a skateboard and you went uphill, you'd slow down. And if you went downhill, you'd speed up, right? Well, same thing with your airspeed. So when you go up, your airspeed should slow down. When you go down, your speed should speed up. But if it's acting like an altimeter, if you're going up, you show an increase in airspeed. And you're like, wait a minute, I'm pulling up. I should be slowing down. But that's showing something speeding up. You probably have a blockage somewhere in that line going to that airspeed indicator, or somehow both the drain hole and the airspeed indicator are both blocked. So that's why it acts like an altimeter. Or if you go down, it should speed up, but it's acting like an altimeter, so it's going to show decreasing airspeed, which doesn't make sense if I'm going downhill, quote unquote. So that's what that means by that. So if you climb, it's going up. If you descend, it's going down. What about static ports? Those are pitot tubes. So static ports affect all 3 pitot static instruments. So static ports are blocked, but the pitot tube is clear. So let's think about that. They're both blocked, but the pitot tube's clear. Well, the airspeed will operate, but it won't be correct because it doesn't have the correct air pressure coming from the static port. So it'll still kind of work, but it won't be super accurate. The altimeter will freeze because remember, altimeter measures the difference in change in static pressure. There's no change. All the air is sealed now inside of that altimeter. So therefore, it's not going to change. So it's like, oh, you're holding altitude perfectly, when meanwhile you might be doing this. And it's just not moving because all the air is stuck in there. It can't measure the change. That's what the static does. It just measures the outside air pressure, and now it's frozen, so there's no more outside air pressure coming in. So it's like, oh, you're not changing altitude because I don't sense any change in air pressure. And what about the vertical speed indicator? It'll stay at 0. It won't change either. It'll just stay there and say, well, I don't sense any change either. All right. So all right. Well, that is the end of this part on the pitot stack system. The next section is on gyroscopic instruments, and we'll learn what gyroscopes are and how they actually work and everything like that. Yeah, so make sure you have your notes filled out from this one, and we'll move to the next one in the next video.